As we speak, our night sky is undergoing a metamorphosis that will leave it unrecognizable in a matter of decades, if not years. Astronomers worldwide have raised the alarm. Experts like Neil deGrasse Tyson have just confirmed that Polaris is about to explode, and the story behind it is harrowing. Its central presence in the night sky defines its special position as the North Star. Until now, Polaris was the one constant stargazers, navigators, and astronomers could always count on. This may change soon enough, and with it, our night sky and astronomical measurements may never be the same again. Join us as we unveil the gravity of this threat and what it means to us all. Let's explore the story of Polaris as it nears its end. Polaris has long been seen as the guiding North Star and has held a revered place as a guiding beacon for astronomers and navigators for centuries. Its steadfast presence in the night sky has been a cornerstone of navigation using the night sky. But this may all change in the blink of an eye. A recent research paper presented by the esteemed Royal Astronomical Society on September 2023 has cast a shadow of uncertainty over the fate of this celestial luminary. The star is on the verge of exploding and forever disappearing from the night sky. Before we dive into the implications of this revelation, let's take a look at the star in question. Polaris, also known as the North Star or Pole Star, holds a special place in the sky due to its proximity to the celestial North Pole. It sits almost directly above the Earth's North Pole, making it appear nearly stationary in the northern sky. It's located in the constellation Ursa Minor, also known as the Little Dipper or the Small Bear. Polaris is a moderately bright star, and in terms of size, it's a yellow-white supergiant star, considerably larger and brighter than our Sun, but of course much farther, with a radius estimated to be about 40 times that of the Sun. Polaris is often perceived as a solitary star, but it is actually part of a complex triple star system. The primary stars are Polaris AA and Polaris AB, appearing as a single star to the naked eye, with a third companion, Polaris B, orbiting the binary pair. The interactions among these stars create a gravitational pull, shaping their orbits and influencing the behaviors of each. Such intricate dynamics also affect the luminosity and characteristics of the stars involved. Any disturbances in these interactions can thus lead to irregular variations in the star's luminosity or pulsation patterns. However, the exact mechanisms and intricacies of these interactions are not yet known. What we do know is that since Polaris is situated some 323 light-years away, the light from Polaris takes approximately 323 years to reach Earth. This means that the light we currently see from Polaris is as it was 323 years ago. Given the distance, if Polaris were to explode today, we wouldn't know about it until 323 years from now. By the time we witness the event from Earth, it would have occurred over 3 centuries in the past. Of course, the predictions made by scientists are based on the empirical evidence we see right now, which means that Polaris could have already exploded, and we simply haven't seen the light from that event yet. Historically, the North Star's importance extends across various civilizations and eras, imparting significant cultural, navigational, and symbolic value. Its stability and fixed position near the celestial North Pole have made it an invaluable navigational aid for ancient mariners and travelers. It served as a guiding beacon, allowing sailors to orient themselves and navigate across seas and lands. Since its position nearly aligned with the Earth's axis, this made it a reliable reference point for determining direction, especially in the northern hemisphere. Across cultures, Polaris holds symbolic importance. In some societies, it represented constancy and steadfastness. It is also seen as a pole star that has remained fixed amidst the celestial dance of the night sky. In myths and folklore, it often symbolized guidance, stability, or a celestial anchor. Polaris's fixed position in the night sky also made it crucial for astronomers. It served as a reference for observing other celestial bodies, aiding in the study of the night sky's motions and patterns. As a Cepheid variable star, Polaris displays periodic variations in brightness, and this in turn helped us uncover important discoveries about stellar properties and the nature of variable stars. This characteristic also made it pivotal in determining cosmic distances and calibrating instruments. These pulsations exhibit a predictable pattern. At least that is how the star behaves normally, allowing us to predict the pattern with ease. However, recently, the star has deviated from this expected behavior. This unsettling irregularity in its pulsation cycle has baffled astronomers, prompting a closer examination of this celestial anomaly. Instead of following a predictable pulsation pattern, Polaris has begun exhibiting an erratic and unpredictable cycle of dimming and brightening. Scientists have now begun raising alarm over the issue, stating that the star may be on the verge of the end. This is consistent with the pattern of behaviors observed when a star nears the end of its life. The progressive elongation of Polaris's pulsation period, which was traditionally stable in its cyclic dimming and brightening, can be attributed to the interactions between the star system that we perceive as one. On our end, we can observe that the annual increment in the pulsation duration stands at 4.5 seconds. This may not seem like much, but it's a big deal. Some astronomers have offered conservative deductions, stating that perhaps the gravitational interplay between the Polaris stars may have induced these fluctuations in Polaris's atmospheric conditions, directly impacting its pulsation patterns. However, others are not convinced. They believe that the star will explode in the near future. And there is reason for suspecting as such, since Polaris's enigmatic behavior bears striking resemblances to Betelgeuse. Like Polaris, Betelgeuse, a prominent star in the Orion constellation, has exhibited perplexing irregularities in its luminosity, leading to speculation about a potential imminent explosion. Many experts have already raised alarm about the star's inevitable end. The fluctuations observed in both stars' brightness and patterns mirror each other, drawing intriguing parallels between their behaviors. Cepheid stars, in their twilight stages, showcase such patterns in behavior before reaching the culmination of their life cycles. These celestial entities, while pulsating regularly for eons, undergo peculiar changes in their luminosity as they approach the end of their stellar journeys. NASA's attention was captivated by the anomalies exhibited by Betelgeuse. The agency's heightened concern regarding Betelgeuse's potential explosion contrasts with the observed irregularities in Polaris. While NASA has expressed considerable interest and vigilance over Betelgeuse's unusual behavior, similar scrutiny and concern have yet to be officially announced regarding Polaris. Cepheid stars embark on a grand journey through various phases in their evolutionary cycle. Newborn stars have relatively low temperatures and brightness. Following this, they progress into the main sequence phase, marked by nuclear fusion, where they remain stable for billions of years. Eventually, as their hydrogen fuel depletes, they transit into the red giant phase, characterized by a rapid increase in temperature and brightness. The red giant phase witnesses a dramatic surge in energy output before culminating in a catastrophic explosion. They shed their outer layers in a dazzling display known as a supernova. Post-explosion, what remains is a compact, dense core known as a white dwarf. Based on Polaris's irregular pulsations, scientists have predicted that the star has entered the stages of helium depletion that are observed in Cepheid stars nearing the end of their life cycles. As a Cepheid star exhausts its stable helium supply, the star undergoes erratic pulsations, causing fluctuations in its brightness. This depletion triggers a series of events leading to irregular light emissions, potentially reflecting the depletion process occurring within Polaris. It is, however, important to note that while these irregularities align with behaviors indicative of Cepheid stars in their twilight phases, definitive indications of Polaris nearing the ultimate stage of its life cycle remain inconclusive. Astronomers continue to analyze and interpret these irregularities in pursuit of understanding Polaris's impending fate. If Polaris were to go supernova, it would likely be a spectacular event in our sky. The star would suddenly become incredibly bright, potentially outshining the moon and becoming one of the brightest objects in the night sky. This could last for days, weeks, or months. The star's appearance might change drastically. It could transform into a brilliant point of light or a transient object, possibly developing colorful hues before fading away. The visual display might temporarily alter our perception of the familiar pattern of the Big Dipper or Ursa Minor, as Polaris is the current North Star and a part of these constellations. As for us, well, rest assured that we'd be perfectly safe. Considering the mass and distance of Polaris, the Earth would likely be safe even if the star were to explode. Visually, while a Polaris explosion might not be as striking as that of Betelgeuse, it could still be visible to the naked eye for long and outshine nearby stars. Astronomers and observatories would certainly take notice, and the scientific community and stargazers worldwide would be intrigued by the phenomenon. Nonetheless, the specific visibility and impact on Earth's atmosphere or surroundings would be less significant compared to a closer supernova event. But what about the star itself? Upon the precipice of a potential supernova event, what will be the post-cataclysmic fate of Polaris? Let's get one thing straight here. While giant stars usually end their lives with a supernova, this will most likely not be the case with Polaris. Normally, when a massive star goes supernova, a colossal explosion occurs within it. This event marks the final cataclysmic stage in the life of that star, resulting in the dispersion of heavy elements and sometimes leading to the formation of neutron stars or black holes. This process involves a complete collapse of the core in a high-mass star, which has to be around 8 times the mass of our Sun. When such a star exhausts its nuclear fuel, it can no longer support itself against its own gravity, causing its core to collapse. This collapse triggers an intense shock wave that races outward, causing the star to explode violently. Based on how exactly they proceed, supernovae are broadly categorized into 2 types: Type 1 and Type 2. Type 2 supernovae occur in massive stars with complex layers, where the core collapses and the outer layers are expelled explosively, resulting in a burst of light and energy visible from vast distances. This is more common of the two. In contrast, a Type 1 supernova occurs in binary star systems, where one of the stars is a white dwarf. One possible scenario here is that the companion star expands and material from it gets thrown into the white dwarf orbiting it. When the white dwarf accumulates enough mass from the companion star, reaching a critical limit of roughly 1.4 times the mass of the Sun, it undergoes a nuclear fusion reaction, leading to a sudden explosion and the release of an immense amount of energy. In another scenario, if 2 white dwarfs are in a binary system and their orbits decay due to loss of energy, they can merge. The combined mass exceeds the critical limit, initiating a similar runaway fusion reaction and subsequent supernova. These Type 1 have a consistent intrinsic brightness, making them useful as standard candles for measuring cosmological distances. Following a supernova, the collapse of a star's core will birth either a neutron star or a black hole. A neutron star is characterized by its staggering density. It encapsulates approximately 1.4 to 3 times the mass of our Sun within a confined space, comparable to a modern-day city, not more than 12 miles or 20 kilometers in diameter. They predominantly comprise neutrons, which are subatomic constituents nestled within atomic nuclei. In contrast, a black hole is infinitely dense, possessing a gravitational pull of such immense strength that even light fails to escape its grasp. This is why they appear black in the celestial expanse, devoid of any detectable emissions of radiation. However, Polaris won't end its life this way to become a neutron star or a black hole. Why? Because Polaris is not massive enough to end its life in a supernova explosion. It's a Cepheid variable star which measures about 5 times more massive than the Sun. This may seem big, but it's not big enough to undergo supernova. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transformation won't result in a supernova, but rather a serene conclusion as it evolves into a small, extremely dense stellar remnant. A white dwarf is the remnant of a low or medium mass star that has exhausted its nuclear fuel. It's incredibly dense, about as massive as the Sun, but compressed to the size of Earth. This occurs when the star runs out of fuel for nuclear fusion and collapses under its gravity. When it does so, we will no longer be able to see its remnants from our planet the same way we observe the star today. Drawing parallels between the anticipated effects of Polaris's burst and historical supernova occurrences offers valuable insights. We can compare our expectations with well-documented supernovae and explosions, like SN 1054, Crab Nebula, or SN 1987A, examining the resulting phenomena such as the formation of nebulae or the release of cosmic rays. Evaluating potential similarities in luminosity variations, ejection of elements, and impact on surrounding celestial environments provides a basis for understanding Polaris's potential aftermath. Contrasting anticipated outcomes with observed supernova events helps us predict the fate of Polaris. Observations from recent supernova, like SN 2011 FE or SN 2014 J, can offer valuable data for comparison. Analyzing the light curves, spectra, and remnants from these events and projecting similar characteristics for Polaris's anticipated burst can assist in predicting the potential evolutionary stages of the resulting celestial remnants. To make a definitive comparison, scientists examine the differences in the mass, composition, and speed of ejected materials between Polaris's anticipated burst and other observed events. Assessing whether Polaris's burst might lead to the formation of nebulae or distinct elemental distributions will certainly enhance our understanding of its unique characteristics. Examining how Polaris's burst may differ from or resemble other supernova phenomena will also involve analyzing the evolutionary stages of the stars leading to their explosions. Here, our goal is to compare the mass, metallicity, and evolutionary paths of stars in the pre-supernova stages, and of course to relate them to Polaris. This will offer insights into potential disparities or similarities in their explosion mechanisms. There is another area too. This is the one that has sent shock waves across the scientific community. We must evaluate the pulsational variability of stars nearing their end stages, much like Polaris, against observed supernova precursors. This can allow us to gauge similarities or deviations. Assessing whether Polaris's irregular pulsations share characteristics with other stars approaching their explosive endpoints enhances our understanding of the potential burst mechanism. Of course, this part we already know. This comparative analysis between Polaris's anticipated burst and historical supernova and smaller burst events is sure to help us predict, contrast, and examine the potential outcomes of this upcoming event. This will provide us with crucial insights into the uniqueness or commonalities of this celestial event within the cosmic context. However, it would be foolish to jump straight to a conclusion here. Despite meticulous observations and extensive analysis, astronomers find themselves puzzled. While the irregularities observed in the behavior of Polaris defy conventional understanding and persist as a perplexing puzzle, they elude a complete explanation. After all, predicting exactly when a star's life will end is no small matter. The perplexing nature of Polaris's irregular pulsations beckons for deeper scrutiny and investigation. Astronomers recognize the imperative need to delve into the underlying mechanisms responsible for the unprecedented behavior exhibited by this celestial entity. Unraveling the unique conditions driving Polaris's irregularities holds the key to advancing our comprehension of stellar evolution and behavior. Polaris is a steadfast reference point for telescopic calibration and celestial navigation. It assumes paramount importance in astronomical endeavors, and perhaps it is this importance that has created a sort of cognitive bias among those who feel that the star will persist. Or maybe the heightened excitement about Betelgeuse has done it for the other side. In either case, the looming uncertainty surrounding the future and the prospect of Polaris's potential burst poses substantial concerns. The recent revelations from the Royal Astronomical Society have highlighted a new area demanding intense scrutiny and research. The enigmatic behavior exhibited by Polaris underscores the criticality of deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding the irregular pulsations, recognize the necessity to unravel the unique conditions triggering this anomalous behavior, and present a concrete answer. But what is that answer? Only time will tell. On our part, all we can do is advance our comprehension of the underlying mechanisms shaping Polaris's irregularities. If Polaris were to undergo a catastrophic event, the loss of this crucial reference in the night sky could significantly impact the accuracy of ground-based telescopes and celestial measurements. This would force us to recalibrate our ground instruments and also impact the accuracy of astronomical assessments. An irreplaceable loss indeed. The anomalous behavior exhibited by Polaris has unveiled a realm of uncertainties in the astronomical domain. The looming possibility of its impending burst calls for heightened vigilance, dedicated research endeavors, and a concerted effort to grasp the unique celestial intricacies shaping its erratic behavior. Thanks for watching. Don't miss this video you see on your screen right now. It's truly unbelievable.